let's come to the next part, which would be verification testing. The typical project that we would have in standardization would be the exploration. There's a CFP, then we have this working draft, commentary draft, final commentary draft, draft international standard process. And after that, basically after the finalization, or maybe also somewhere around this transition, the verification test process would start, which is meant to double check what has been achieved. So are the requirements achieved, and specifically as part of those requirements, are the compression goals achieved? This is something that's very important because it can be used. Well, since it's public record, it's basically something that can be used to advertise the new scheme to be adopted by industry for their products. So having this is a very helpful tool as a completion of the standardization process and giving test data at hand that may help decision making in the industry. And the main tasks are that we have to build something which is trustworthy and reliable and usable for this purpose. So what we typically do, we do something which is not, they call the common testing scenario, which means we are not like with common testing conditions that have been used to develop the standard, but we use something apart from that. We specifically use something that would be representing relevant use cases. So like for video coding, it would be like streaming, conversational applications, but also others. And the test sequences, of course, must not be the same that have been used in the development process. The rates, so the quantizer settings, everything would be different. What might not be different, but similar would, for example, be the encoder configuration, because typically the configurations of the common testing conditions kind of reflect very typical scenarios of use cases. So that's something that may be used, but it's still sufficiently different from what has been done in the process, in order to avoid that there would be some bias, for overfitting reasons or something like that. And also, what we typically try to do is that we would have a quality range that's covered that may be a little bit more than what the application needs in order to get a full characterization of the scheme. Right? So if you think of UHD video, we might not go down to very low qualities because we would do something else, we would switch resolutions, whatever. But still, it's interesting to know how the system behaves under adverse conditions, and this is considered to be useful information for the outside world as well. So since the way or the steps that would be needed for verification testing have been challenged a bit in the starting of AG5, we decided that we would define some guidelines for verification testing, and those are basically, it's a relatively short document, so just 4 pages, where the core elements actually are already captured on the first 2 pages. So it's really a relatively short document, but it makes very clear what we have. So what is the purpose and the goals of the verification test? What are the procedures? What is the selection criteria for test material? What should be regarded when bit streams or breakpoints are, and then the breakpoints are selected? How the visual test should be conducted, and how the reporting should be done. And all those things are very relevant in order to make this information that's published in the verification test something that's trustworthy, it's reliable, and that's also reproducible. And this is something that's very, very helpful if the verification test has the qualities, because it sends a good signal to the outside world. So we should not exaggerate the gains by searching for some sweet spots. Of course, we should also not over critically select material where things don't work, but put something which is meaningful and useful in a fair manner. That's basically the approaches that we try to follow, and that's what we did. We have a bunch of such activities which already have been completed. Just list the parts. There is some of them. So we have the EVC and LCEVC schemes that were kind of inherited for AG5 because they already started before came to life. The first big one that we did was VVC, and I just have some curves here. You see the curve, the pool curve for the MOS values over bitrate, and for the HEVC test model comparing to the VVC test model. That's HN and HEM. Then the third thing that you see here was the VV-Inc. Open source implementation. That was also part of the game, but for the first purposes, it's just important to look at the orange and the blue curves. Because what was concluded just beyond the rate savings was something about 40%, which seems to be realistic. And similar results were achieved for HDR and also for 360, where we have some this kind of stuff data. So those are results which are considered to be quite helpful and useful for the advertisement and also the adoption process of the standard in the outside world. One more example would be immersive video. That was the last one that we did, which is also interesting in the sense that we typically do PCR tests, as I mentioned before. Here we decided to go for the ACR with the argument that the ground truth in this case is hard to get because of the influences of the render and so forth. So it was decided to rather go for the absolute category rating, the degradation category rating. Where in DCR, maybe just to remind people who might not know, we would compare the coded version to the original, and then we want to measure the impairment, which means that we know what would be the best thing achievable, and we want to measure how much the coded version diverges from there. And we basically project that to the 11th grade scale. In ACR, we have absolute categorization. We don't have a reference, so the viewers just get the original, they get the coded versions, and they just have the interpretation of the scale, and they shall score everything there. And then, if you want to compare, you basically have the distance between the best reference, what you would get, or the coded versions. And this is actually what you see here. These two examples that I included in the slides. And so the main messages are very easy. So you see the green curve, that would be the performance of the best reference, and then we see different variants. So in the upper case, that's a sequence with natural content with and the geometry only profile, the geometry absent profile of this, which perform significantly better than the anchor, which was NB HEVC, so multi-view HEVC coding. And you see that you get quite some saturation for those. It's already at relatively low bit rates compared to what we're looking at, while the geometry absent already reaches overlaps in the confidence intervals as the best reference. So meaning that the coding process itself would not provide you gains anymore, but what might be possible, and it's something that you see here from the scale, that the rendering process that is used, which would leave some headroom for further improvements. And similarly here, this was a synthetic sequence. We see that we basically get some linear increase into it. Again, here you have quite some substantial gains that are observed. And this is kind of the information that we try to share and try to advertise in the outside world for those tests. Organizationally, maybe that's something that I actually didn't mention on the slides. 85 would conduct those tests and will prepare the test scenario together with the working group, then conduct the test and then hand over the data to the working group, who will then produce the output document. That's something that you see down here. So you ask the working group for output document. That's then the final report on this activity. What's the legend is scalability. We will look at that a little bit, and a testing activity, which is not specifically a verification test, but a mere evaluation for the film grain characteristics. The difference may be subtle, but it's evident. So verification tests are something that would be done for standards, while In the film grain case, there is not a specific standard, but it's an SAI message, and it's a technology that can be added on top of regular standards. So this is something that would not be classified as a verification test in that sense, but rather just a visual evaluation, which is helpful nonetheless. As you know, as you might know, there's a technical report on film grain characteristics being prepared by JDET. This kind of accompanying this viewing activity. Okay, so what's on for multilayer coding? First one category. So for multilayer, we have 4 categories. First one is basically the efficiency of spatial scalability coding. Here the focus is on 1.5 and 2x spatial scalability. And the question is basically to what extent, what is the price for having that kind of scalability? The second one is the so-called quality ladder. That's something that's used in streaming a lot, where we would have a meaningful combination of resolutions and rate coins, or the rate set, and then, for example, Dash could be used, or any HTTP adaptive streaming methodology could be used to pull data from a server. The latter basically provides the ability to adapt to network conditions and other events that might affect the quality of the transmission. Right, and the scenario here is, or the use cases that scalability may help to serve to save some storage space on specifically what we could call the edge storage. So the CDN, the content delivery network, basically on the last mile when we would push the data to the specific users, where you have to store all the videos that might be called. There, if you use scalability, you can save something. And I think the savings might be around something like 20%, so it's quite significant. Okay, third category would be content layering, where you would might have something like so-called sub-content, so overlays to the video and things like that, which would be supported in a scalable stream. And the benefit of that is that you can support this technology on the video stream level, right? So typically this is a topic that's handled on the systems layer, but if you want to, you can also do that on the elementary stream level. So basically having a scalable video stream that would provide you the version with and without this kind of layering, exploiting thereby the functionality of the multi-scale streaming. And the fourth category, this is the one with the least activity so far. That's about dual view coding, which is so specifically like stereo viewing of the 2D video, and which is on the roadmap, but not yet developed so much. Just to give you some insights, currently what's considered our video feedings that we have here, we did some expert viewings to settle on our bit rates, to settle on or to confirm selection performances, and sometimes this expert viewing, which is basically is a pre-step before we would do a formal evaluation and before finalizing the plan. This is very, very healthy to do because what we, for example, found just at the last meeting in Geneva, that the objective performance, for example, of just upscaling the base layer may look very different from what would be rated subjectively. So this is something that leads to the investigations, because the inspection of the data showed us that the gain of detail by single layer and also scalable version is clearly better than what would be there in the upscaled version, the base layer. But then there are other artifacts that overrule this kind of these gains. So next evaluation step, the next development step will be to tune the coding and such that we don't have that issue anymore in the performance of that. But basically, this is kind of something like the last step before we would run a final call, final round of objective of formal subjective evaluation, and then could produce another verification test report on that. For the second category, the quality letter, this is a work in progress, but just to show you what's on there. So you have a draft table of how things might look like. This is inspired by the HLS screen provided by Apple, which does not yet have the VVC category. And then you have a suggested set of bit rates for VVC. And you see that if you look at the HDR increase, sort of the relations, it's kind of just trying to propagate what has been done with ITTC now to the bitrate range of what is considered to be useful for VVC. You see on the right here, there's some examples where you have the YPSR, so the Luma analysis for the causal sequence, where you have then different breakpoints or different quality metrics on the different resolutions. You see down here the resolutions that are evaluated, and then what we basically try to do is something like the convex hull of the streams to provide you a good coverage of the MOS scores at the optimum bitrate resolution combination for that point. And that's basically what is currently evaluated and investigated. For the content layering third category, this is just an illustration. There was the very nice demo provided in Geneva, which is shown here. So you have basically a small tablet that would be used as a controller. Then you have a streaming device that basically would provide the data using the MMT format, and then there would be a multi-layer VVC decoder, which is then basically controlled by this tablet, and then the output would be rendered to a 4K monitor. And here's just one of the examples of how this content layering might look like. In this case, you see that the base layer covers one video, and then you could activate, or if you activate the second layer, the enhancement layer, then you see that the base layer is actually downscale to a portion of the video, and then there's, in this case, there's some sign language which is added for people who might need that kind of information. And the connection is basically that since DVC allows the enhancement layer also to be smaller than the base layer, by concept, you can basically exploit the information in this base layer to have a very cheap representation of this area in the enhancement layer. So overall, you have some benefit in the overall coding cost from this kind of data. And there were other use cases, and if you're interested, you're invited to look up the input contribution AE 285, but there also will be a report being prepared from David that will more formally present those results. For the build gain, maybe just to move on, this is actually something which is very different in the way testing may be done. I think I don't have the main goals. There we only have two categories, maybe just to sum that up. One category would be using film grain technology to achieve better compression performance. The other one would be using film grain synthesis to emulate actual noise in the video stream, and that noise would be sufficiently equivalent to what is the intended noise in the video. So this is specifically important if you consider movie content, big films that would have a certain aesthetic intent in the artificial or actual film grain or film noise that you have in the video. That is something that we would like to bring to the customer, but coding that is very expensive. So removing it, coding without the noise, and then synthesizing it at the receiver side would be a very good thing. And this is basically the intention to study the capabilities of that technology. The film grain on its own is something which is about 20 years old already. and has been there around quite a bit, but so far has not been thoroughly tested in MPEG for these purposes. So in this sense, it's something like a relatively new activity for the standardization committee. It's not so much new technology that's actually considered. It's just that there's film grain technology available also in other schemes that are around, and so the intention to just demonstrate what's possible, for example, with VDC, might have been inspired also by this kind of activities. What have we done so far? We did expert viewing as a trial run to see what's going on towards what's called goal 1. So that's the benefit of film grain tools for compression. And what was tested here was the QP selection for the current set of sequences. You will see what that's about in a minute. The confirmation of what we would use as a lowest QP point, so the best quality, which would just preserve film grain. And then the last thing would be some indicative rate shading checks for the film grain activity. And so since we are talking about depending on what we do, so for the QP selection, we actually went for a DCR method. So you see the viewers would see the original sequence with its noise, and then they see the coded version. And then they are supposed to judge the overall impression. For the lowest QP point, where we are at very high qualities, we decided to go for an A/B comparison, so that we more granularly can decide on which one would be better and which one would be worse. And so the results for those two tests are now shown. So this is first the DCR result, where we see at the very low end, typically we have no or some little benefit, but it's not super significant. If we go to the higher rates, then things might be different. So you can see here for the adenosine, for example, we had some significant benefits at the higher rate points, and then some saturation effects in the upper end. And for the old town cross sequence, you see that there's a clear benefit at the higher rates with a breakdown if the bit rates become too low. So those are actually very promising results. Currently, what's going on here is the question on what kind of content should we have. So this set, we have Crowd Run and Old Town Cross, which are both analog video, so digitized by scanning the film. So that's actually original film grain noise, but also overlaid with film artifacts, which are like scratches and things like that. And the dinner scene is a scene that has been captured by a digital camera, and then has some artificial noise. So that's something that needs to be covered as well, because that's basically the way how state-of-the-art video would be produced. And having artificial grain means that also different types would need to be considered. And so there's a lot of discussion currently going on how to evaluate that. We had some contributions in the last meeting, one from Apple, which was very nice, where there would be something like a clean video, and then they promised to provide some versions with different amounts of film grain added, so that we could study the effects of the film grain, and also the impact on the compression very nicely, because we have something like look at it from the coding from the noise perspective, you would have a ground truth that would have additional noise. So that's very interesting, and we'll continue further. The other aspect that I mentioned was this A/B comparison at the very, very high bit rates. And here, what you see here, this was a A/B comparison with 5 scores that could be given. So you could say that the two are equal. There are the one is better than the other one, or it's clearly better. That was basically the options that you would have. And you see here the comparison of the version without film grain synthesis, so the plain coded version compared to the original. And what you see is that the QP has been chosen such that the viewers rated those to be equivalent. That's basically the message that we have here. While for the second one, where we compare the FGS version against the non-FGS version, you see that you have a slight drop here for the FGS version, but not super significant. So ideally, also those would be rated similarly, because then we would say we are on par. But you can see that, I mean, this is kind of a very optimistic way of testing it. And this is something that you also see from those numbers, where you see that you have a lot of bit rate that can be saved if you just synthesize in this range. But this is not something that we would consider realistic. So the intention is that we would do a next test, maybe where the non-FGS points would have a little loss compared to the FGS, so that we are more conservative in the bit rate savings that we would have here. That's something that would come in the next steps.